So it's our pleasure to have Liana speaking today. We were together at some point in Oxford, and it was a lot of fun hanging out with all the people there in much more cheerful times. And now Liana is back to the UK now at LSE, and she'll talk about Size Ramsey numbers of powers of hypergraph trees. So nice to have you, Liana. Thanks for giving
thanks
the talk.
a lot. I'll talk about the joint work with Alexei Pokrovsky and Shoham Ledster, who are both at UCL. And for the most of the talk, there will be a lot of, I will review what's known about Size Ramsey numbers and give a history of these numbers and the research that has been done. And then we will have some time to also think about, I'll talk a little bit about our proof ideas as well. Okay, so the beginning is about a bit slow so that we get to get into the mood. Right, so Ramsey numbers, I guess everyone knows about them, but for two graphs, GH, we say G is H Ramsey. And I will denote it by G arrows H if any two coloring of edges of G, there exists a monochromatic copy of H. For example, this picture here, it's a classic example which we see in the first combinatorics course. It shows that K5 is not Ramsey for K3 because there exists two coloring of the edges of the complete graph on 5 vertices such that there's no monochromatic triangle. So in fact, one can show that also K6 is actually Ramsey for K3, and what that would mean that in any coloring of a complete graph on 6 vertices, there's always a monochromatic copy of the triangle K3. Okay, so the classic theorem of Ramsey, it says that for every fixed T, there exists some large n integer such that Kn is Kt Ramsey. What it means is that for every two coloring of edges of Kn, I can find a monochromatic Kt. And the Ramsey number RT, which a very a topic of a lot of studies in combinatorics, is defined as the minimum n such that the Kn is Ramsey for Kt. So it's a completely different area of research to figure out what is RT. The best known bounds up to some I don't know how to say it.
Sub-exponential terms.
Yeah, sub-exponential terms. RT is known to be between 2 to the 2t and 2 to the t over 2. I mean, these are improved, but all the improvements are little of these terms. So, little of these terms. So it's not, I'm not mentioning those. But yeah, there's like a huge area of research, and this is really central in combinatorics. What today I'm going to mostly talk about is so-called size Ramsey numbers. But before that, let's just generally define what the Ramsey number of a graph H is. So the Ramsey number of a graph H is defined to be, so the minimum n such that the complete graph Kn is Ramsey for H. So RT was just defined to be the Ramsey number of KT. Okay. Actually, it is true that you can also equivalently define this Ramsey number of a graph H to be the minimum number of vertices in any graph G, such that G is Ramsey for H. So these are the classic Ramsey numbers. And the size Ramsey numbers, which were introduced by Erdős, Fodry, Rousseau, and Schelp in 1972, they are denoted by, so for a graph H, the size Ramsey number of H, which I denote by R hat of H, is defined as the minimum over all graphs G. Instead of vertices now, we take the number of edges, such that G is Ramsey for H. Okay, so the difference between, let me just write the normal Ramsey number, it asks you to minimize the number of vertices, basically find the smallest graph, which is Ramsey for H, and the Ramsey number, the size Ramsey number, which I denote by R hat of H, it's when instead of vertices, I minimize the number of edges. Okay, so this would be, this is the definition of size Ramsey numbers. And now let me go a little bit towards the history of size Ramsey numbers. One easy fact before going ahead, let me just mention that I guess I should have written a little bit smaller, but let's try to see if I can do it here. So actually, it's not difficult to see that this size Ramsey number of H is at most RH choose 2, right? Because you can just take the graph, the complete graph on which actually hosts H, which is Ramsey for H. And if you take all the edges there, then that already gives you a bound for the size Ramsey number. So this is an easy fact. We will use this later. That's why I am mentioning this. Okay, some history of size Ramsey numbers. I think this was all started by Erdős in 81. In his paper from 81, he asks what sort of behavior does the size Ramsey number of the graph Pn, which is the path on n vertices, have. He asks whether it's the the first question here is basically saying, is it of order omega n? So it's like much higher order than linear.
Superlinear.
Yeah. And this one is saying, is it subquadratic? So he asked these two questions. And then Beck actually proved that the size Ramsey number of the path on n vertices is of n. So it's linear in terms of vertices. And then he improved the constant in front of it. And then this constant 900 was improved further by Dudek and Pralat in there was a lot of research in between. So here I'm skipping lots of names. But the state of the art for paths is that the size Ramsey number of Pn is at most 74n by Dudek and Pralat. What about the lower order term? We know that by result of Bal and De Basio, it's at least this much. So 3.75 plus a little of one term times n. Of course, finding the right constant here is, I think, a challenging problem. And actually, maybe paths are the only graphs or where we know a lot about the constants. Usually it's much more about whether it's, what is the order of magnitude, rather what are the constants, Okay. A conjecture by Beck from 83, he worked on this path problem and he asked, what about trees? So if I take a tree on n vertices, what can I say about its size Ramsey number? And he said that he asked whether if I take any tree on n vertices and maximum degree d, is it true that the size Ramsey number of this tree is going to be linear? Okay, here you might wonder, why is it that we are asking the graph to have bounded degree, the tree to have bounded degree? So exercise afterwards, if you want to have a bit of fun. If you look at this graph, I call it double star. So what is it? It's two vertices joined by an edge, and then from each one of them, you hang n leaves. So let's call this dsn. Then you can show that actually the size Ramsey number of this graph is already quadratic. And that's because the graph has unbounded degree, the tree. So this conjecture of Beck was confirmed by Friedman and Pippinger. And what they showed is that the size Ramsey number of entire family of trees on n vertices and maximum degree d is linear. So this is really interesting. It was a very, I think, important step in size Ramsey numbers, and a very beautiful paper, I think ahead of its time. So anyways, what is T and D here? This is all the trees. So this is the family of all trees on n vertices and maximum degree D. So what they showed is that so you fix your D, and you show that if I take any tree T in this family, then the size Ramsey number is going to be linear. But what's even more important is that the graph that's hosting all these graphs is actually one unique one. So it's a kind of a universality result in the sense that the same graph, the same host G, which is Ramsey for all trees in this family. So, and in fact, this graph, which is the host graph, is just a random graph, except we remove large degree vertices. I'll talk more about that later, but yeah, so this was very important work. And then a question of Beck from the same paper, actually. He said, okay, well, we saw that graphs of large degree, unbounded degree, we can't ask them to have linear size Ramsey number. But what about if I take any graph which has bounded degree? So his question was, if I have a graph G, n vertices and maximum degree d, is it true that the size Ramsey number of G is bounded by some constant depending only on d times n? And so first of all, what can we tell at all about this size Ramsey number? Already back then, it was known that this number must be subquadratic. Why? A result of Schwatal, Rodol, Semeredi, and Trotter from say around the same time say that for any graph G, which satisfies this property, meaning it's a graph on n vertices and it has bounded degree, its normal Ramsey number is linear. What that tells you is that if you take the size Ramsey number of such G, then it's at most RG choose 2, right? This was the easy fact we saw before, which means that this is of n squared. So before Beck's question, I guess he knew that it's any graph G of bounded degree has size Ramsey number somewhere between linear and quadratic, but nothing. We didn't know if actually there are such graphs which have bounded degree and nonlinear size Ramsey number. And that's where the work of Rodol and Semeredi comes in. And they showed that actually Beck's question has a negative answer. What they showed is that there's actually a family of graphs denoted by Hn. So these graphs have n vertices, maximum degree 3, and their size Ramsey number is n times log n to the some power. So we cannot expect that every graph on of bounded degree is going to have a linear size Ramsey number. This paper I highly recommend to read. It seems a bit of a magic, but it's very beautiful and nice. Again, this result is very important. In fact, we don't know of any other graphs which have this property. This is the only construction so far we know of which of bounded degree graphs with unbounded, with nonlinear size Ramsey number.
Liana, can I ask you, like, what kind of graphs are these? Like, is there a way to sketch this?
Yeah, so these graphs are, so they take some large trees, binary trees, and these binary trees are, so the same binary tree, and then you take many, many copies of them, and the number of copies is how many ways you can put the Hamiltonian cycle on the leaves. So you take basically all the possible orderings of the leaves of the same tree. That's how many copies of these guys you are going to have. And then what you do is that, I don't remember, I think like you somehow just join the roots of these trees via paths, something like this. I forget the exact construction, but yeah.
And probably you form some Hamiltonian, and you form Hamiltonian cycles on the
so
leaves for each copy.
On each here on the leaves, you see Hamiltonian cycle. That's what they use.
Okay, interesting.
Yeah, but you can imagine, right? This Hamiltonian cycle, I mean, you order the vertices, the leaves, and then you take all the possible orderings, and then you take the cycle. Yeah. So it's like all different. Yeah. So yeah, that's the graph. And the same construction is also generalized to hypergraphs. We'll talk about that too. But nothing else is really known. It's very interesting. And I think someone has to prove something here. Show some other graphs which have this property. Okay. What they did conjecture, though, that this log n is not really what the right bound is, meaning that there must exist graphs such Hn. And here I don't even want max degree tree, any max degree, any bounded degree, such that their size Ramsey number is actually n to the 1 plus epsilon. So for some absolute constant. But again, nothing is known about this conjecture. From the other end, meaning from the upper bounds, what we do know is that if you give me you fix your maximum degree d. Oh, here there's a mistake. For any epsilon less than 1 over d, any graph G with maximum degree at most d, and then vertices, its size Ramsey number is bounded by n to the 2 minus epsilon. So we are actually subquadratic for sure for bounded degree graphs. This is a result by Koyakawa, Rodos, Schacht, and Zemaredi. And this epsilon here also has been improved for some graphs, like triangle-free graphs, for example, was improved by Raikon and Adov and David Conlon. And yeah, I mean, for some graphs, I think this epsilon is improved. Yeah. So, okay, now what other, so we talked about paths, we talked about trees. What other graphs this size Ramsey number have been studied for? Cycles. So this was a result of Haxel, Koyakawa, and Ruchak in 90s, who showed that, the size Ramsey number of the cycle is also linear. Let me just mention that one thing is, not for all of the, all, what do I want to say? I want to say in all the mentioned cases, the host graph G, for which G is either Ramsey for Pn or the tree or the Cn, G is basically the random graph GMP, where you take, so your number of vertices is something like a big constant times n, right? So you want to still keep linear number of vertices, and the probability P is something, another constant over n. And what you do is that you delete any from GMP, any vertex which has large maximum degree, and then you can show that the obtained graph will host both the trees and the paths and the cycles.
And for the regular graphs, the upper bound, it's also GNP or it's different? Like with it's obviously bigger
one.
P. Yeah.
That's a good question. I would think that it is, but I don't know the proof of this result, but I think it probably will be.
Okay.
Yeah. Or some blow up of an expander, something of that form. Was nothing really, no other host graph are known. Okay. And then I don't know what happened. For about 20 years, this size Ramsey numbers were not studied that much. And then David Conlon at a workshop asked the question, what about powers of paths? So what's the power of path or power of any graph? It's, so if I have graph G, G to the K is defined to be so it has the same vertex set as G, and so two vertices U and V are in an edge in G to the K, if and only if their distance in G is at most K. So here it's an example of I took the path on 5 vertices, and unless I messed up something, this is the third power. meaning that any two vertices which are of distance at most 3 in the path P5, I connected them by an edge.
It's just, I think it's the second power, but still.
Depends how you count the distance, I guess. Yes. Right.
Well, if the path itself should be the first power of the path, I would say.
Yeah.
Probably, but
sounds good. Yes. See, I knew that I messed up. Okay. So Conlon's question was, you can think about it as the generalization of the cycle problem, because the powers of paths also contain the cycles in particular. So he asked whether for these graphs, the powers of paths, it's a linear, the size Ramsey number is linear. And this was proven to be the case by Clemens, Jensen, Koyagawa, Morrison, Mota, Redding, Roberts. And afterwards, not the same set of people. So I think some people left the group, but Han, Jensen, Koyagawa, Mota, and Roberts showed that actually the S-color size Ramsey number is also linear. So far, I have not told you anything about the S-color size Ramsey number, but you can guess what it is, right? It's instead of taking two coloring of the edge set, you take any S coloring of the edges of the graph G. And again, you define the S color size Ramsey number to be as the minimum over all graphs G, such that, and you take the edge set, the minimum number of edges, such that G is S color H Ramsey, meaning that any S coloring of the edge set of G must contain a monochromatic copy of H. In general, about the S color size Ramsey numbers, so usually they are harder because you have more colors. So again, for path, for example, it's quite well studied. It's known that the size Ramsey number for S colors for Pn is somewhere between omega of S, so somewhere between S square n and S square log S n. So the upper bound is by Krivelev, the lower bound is by Dudek and Pralat, and it's an open question what's the right order here. And yeah, as I said, for powers of paths, it was proven by Han, Jensen, Koyagawa, Mota, and Roberts that also all powers of paths have also multicolor size Ramsey number linear. Okay. Then we worked on the problem of, so what if now you take powers of trees? So in the similar way. So, and we showed with Nina Komchev, Anita Libena, and David Wood that if I take any tree with n verses and maximum degree d, then its size Ramsey number is linear as well. And this we only did for two colors and independently at the same time. Berger, Koyagawa, Maesaka, Martins, Mendonça, Mota, and Parchuk showed that the same is true if you take any color, so for all colors. So again, one thing to note is that all this, in these cases as well, the host graph, it's not really the random graph, because the random graph would be too sparse, but it's obtained by some power of the random graph and then blowing up by like large clicks. I'll talk more about this, but importantly here, you can, the starting point is still the random graph. Okay. Now, and finally, size Ramsey number. And another class of graphs which was also considered are the so-called subdivisions. And what's a subdivision? The Q subdivision of a graph H is obtained from H by replacing every edge by a path of length Q. Here I have the triangle, and I obtained the third subdivision of the triangle by basically you add Q minus one new vertices, and you get like a path of length Q that goes in between the endpoints. So the size Ramsey numbers of subdivisions were also studied before, and very recently, Draganic, Krivelevich, and Nadov proved several results about them. So the first result says that if you take any graph H on n vertices and maximum degree D, then its size Ramsey number of the, not its, but its Q subdivision is going to be bounded by n to the 1 plus 1 over Q. So this actually improves the results of Kohayagawa, Retter, and Rodel. And here, we don't know anything about the tightness of this result, because basically, to know anything about tightness, you would want to know any bounds about the, like any lower bounds. But the moment we think about graphs H as being bounded degree, when you subdivide it, you still have bounded degree. And I just, a few slides before I explained to you that except the Rodel-Samoretti construction, we don't know of any constructions of bounded degree graphs where the size Ramsey number is not linear. So no idea what the true answer is here. And what they also showed is that if you take long subdivisions, so if you subdivide, so here, I mean, if you subdivide by some constant times log n many times the edges of such a graph H, then you can show that actually in that case, the Q subdivision of the graph H has a linear number, has a linear size Ramsey number. And this actually confirmed Park's conjecture. Park worked on this and he proved some bounds, and then he conjectured that this must be, this must be the correct bound. Yeah. Okay. So what about hypergraphs? So far, we have only talked about graphs.
Liana, sorry, before you go in, can I ask you a couple of questions?
Yeah.
So one thing I wanted to ask is there any monotonicity in any way here with the subdivisions? Like, can you, in some sense, guarantee that Q plus first subdivision has smaller Ramsey number than Qth subdivision? Maybe proportionally to the number of vertices or something, I don't know. Or some result of that kind. Because the bound suggests this, of course, this bound of Stakov.
Yeah, I see what you are saying. You are saying you are increasing Q, and then
say if the, I don't know, if the average degree is bigger than 10, then subdividing each edge, adding one bigger subdivision is better. Like one longer subdivision is better than not.
So I don't know of any relation between these guys, to be honest.
Okay.
But there might be something. It's just usually you don't know what's the host graph. So I guess what you want to say is that if you can, if you know that your graph G is hosting edge to the Q, then how you could modify it.
Replace.
Maybe a bit, you blow it up a little bit, and then you can say a few things. But yeah, it's a good question.
Okay.
I don't really have the answer though.
I had also a question about the complete graph actually in this context. Is it clear that, again, since we don't know anything about the exact values or not much, is there a way of saying, say that the size Ramsey number of a complete graph is exactly its Ramsey number choose 2?
Yeah, it's actually a result by I think Chvatal.
Okay.
Yeah, and this thing is you yeah, I mean there is a way you can color you can get exactly this number by you take the color, like I don't remember exactly the construction, but it is in a paper by Chvatal, and yeah, that the complete graph is the graph for which the bound you said, these are the size Ramsey
Test
of
for size Ramsey of complete.
yeah, this for this when this is equal when H is a complete graph.
Okay.
To show this, you take the complete graph on RH number of verses, and you show coloring which does not contain any copy of KT. Monochromatic. Okay. And the coloring, I mean, if you think about it a little bit, you will probably come up with it. It's not so.
Okay. Well, that's nice to have.
You start with the starting point is you start with the coloring for the normal Ramsey number, and then you blow it a little bit, and yeah, I think this is the idea.
Okay. Great.
Okay, so for hypergraphs, the study of size Ramsey numbers have only been initiated very recently in 2017. So there's this paper by Dudek, Lafleur, Moubaye, and Rodel where they started to ask these questions for really basic hypergraphs, and even for those we didn't know much until recently. So they asked what's the size Ramsey number of the path of the R uniform tight path. What's an R uniform tight path? I'm missing my P. So here is my so you take basically n many vertices, and every consecutive R vertices are an edge. So here you have the path on 8 vertices and uniformity 3. Okay, so every consecutive 3 vertices are in an edge, in a 3 edge. And the question was, what's the size Ramsey number of the tight paths? And Lu and Wang showed that for uniformity 3, oh no, actually I'm lying. They showed it for all uniformities R. They showed the bound to be n log n to the R over 2. So it's actually, it was just an upper bound for all R. And then Han, Kayakaba, Lester, Mota, and Parchuk, this paper just, I think, got published. They show that for uniformity 3, the question is valid. So the size Ramsey number of the tight path of 3 uniformity is actually linear. Okay, and then there was nothing else for all other uniformities, really. So our results, our results show various, basically, we obtain different, like many results, and they all come from one main general theorem. But I kind of want to state each one of the theorems first to give some idea of what we can prove, and then I'll state the main result as well. Just 1 second, I want to turn on the light. Okay, so so we basically showed that the size Ramsey number of all tight paths of all uniformities is linear, but we actually showed something stronger. We showed that if you take the kth power of any such tight path, then its size Ramsey number is also linear. Okay, so this was the tight path. You might wonder, how do you define the kth power? Because in the hypergraph, setting, we couldn't actually find any definition generally for the Kate power of hypergraphs. If you have seen it somewhere, please let me know. But for tight paths, this was already, I think, but in this paper by Kohagawa and et al, they did mention this. So okay, what's the Kate power of the tight path? So you take, so you have n vertices, and if you take any r plus k minus 1 consecutive vertices, then you must see a complete graph of uniformity R. Here I have drawn, so for example, if R is 3 and k is 2, then any 4 vertices, right, R plus k minus 1 must be giving me 4. I take any 4 vertices and I have a complete graph there sitting on it, and so on. So every 4 consecutive vertices, this is the picture. And what we showed that, okay, for these graphs also the size Ramsey number is linear. Now, we also showed that a similar, same result holds for R uniform trees. Again, there are many ways you can define trees in hypergraphs, and in the literature there are like various ways. We kind of stick to the definition, which was the most general version we could obtain from the paper by Dudek, Leflore, Moubaye, and Rodel. So we will define the R uniform tree to be an R uniform graph with edges E1 to the EM, such that so every edge you take, EI, if you look, so this is an ordered set, okay? So this is kind of important. If you look at, the intersection of EI with all the previous edges, then this must be of size at most R minus 1. So it kind of says that every time when you go from, the idea here is that like whenever you obtain EI, okay, in this ordering, so you have your graph here and you have all the edges E1 up to EI minus 1 living here. To join, to get a new edge, EI, you have to add one new vertex at least. So that's what the first, property says. And the second one says that actually, if you look at this intersection with all the previous edges, then it must lie in one specific edge. Actually, this intersection could be empty, possibly, which kind of means that these guys could be completely disconnected. You could have like you could have like a bunch of EIs here and then completely disconnected here and so on, right? Because this intersection could be empty. But yeah, so I think this definition should have said something like R uniform forest, but yeah, we just kept whatever definition, whatever notation they used. Okay, but it does not mean this is connected graph, basically. That's what I'm trying to say.
Liana, I have a question. Won't the second condition imply the first condition?
Why?
If it's R uniform.
No, it doesn't imply it. Why would it imply?
Intersection is contained in E sub I0, right? And doesn't equal E sub I0.
Well, I actually, you are saying if you require only second one.
Right, that's what I meant.
But
anyways,
if I change it and say that this is strictly contained the I of 0, then I agree.
But if all the edges are different, or like if the edges form an anti-chain, then I guess what tau means is that EI sub 0 doesn't have all elements from EI.
No.
So then it will. It seems actually that it implies the first condition.
That's actually very interesting. Also, can you explain that again? Because I have not seen it before. So you are saying that if I have this, even without But I need to ask, no?
So this set, which cardinality you measured before, is contained in another edge, but the intersection of EI and EI0 is not the whole EI. So there is an element in EI minus EI0.
Here, like right now, this means that it could also...
It could be equal to EI0, which is okay. It still means that there is a vertex that lies in EI.
Mm-hmm.
Well, it cannot be equal, but we'll deduce it. So there is a vertex that lies in EI that does not lie in EI0, just because edges form an anti-chain. I mean, they are different. I'm just saying that they all have the same size and they're different.
Okay, sure. If you, yeah, okay, I agree. If you request that they are an anti-chain, then yeah, I agree that.
But they should be, meaning you don't allow. It's not a multi. It's not a multi.
Yeah, I agree. You don't. But it's interesting. I did not see it before. So we basically don't need this first one. Okay, good. Thanks.
And I also wanted to ask. So for the trees, maybe it's good if you'll say a few words for normal trees. What this ordering would stand for.
Sorry. Yes.
So for the normal trees, what this ordering would stand for? Like how is there an easy way to I mean, I can imagine orderings, but I think it would be helpful for the listeners.
Or just you mean like
just two hypergraphs for graphs, just for graphs.
Just for two graphs.
Yeah.
Well, it basically means you can just the ordering could be just ordering by leaves, right? So you start from your root, you fix a root, and then you say, okay, the first is this edge. Oops. I believe like you say, okay, I first add this, and then I add this, and then I add this, and so on. I think you go by levels, and that should give you the ordering, I believe. Because every time you add an edge, it only intersects one edge previously. You just add the leaves each time.
Okay, so you have some root. Sorry?
It's called topological ordering, right?
Yeah, I fix the root and I start. So I look at the tree, and the way I can say is that I can just take the hang it from some root and start saying, okay, this is my E1, this is my E2, this is my E3, this is my E4. And every time I just add one leaf to the previous graph. This,
okay.
Yeah.
Cool.
Okay. Yeah, so where were we? So yeah, so basically we can show that also for these trees, the size Ramsey number for all colors is linear as well. Okay, now, okay, and then we could also show the same for the Kate power. Again, we couldn't find any definition of Kate power of a uniform, like our uniform hypergraph. So we kind of generalized this definition that we had for paths. And here it says that, what is it? So I'm going to say that for our graph H, its Kate power is the same graph. It's defined on the same vertex set BH, and edges are any R set, which is contained in some tight path on at most R plus K minus 1 vertices. So it kind of generalizes the R equals 2 case. And right, because R equals 2 gives you K plus 1 versus, meaning that the distance is at most K. And so we showed that for these graphs also the size Ramsey number is linear. So if I have any tree of bounded degree, then so here the bounded degree is again very important, because you can construct trees based on this Rodel-Semeredi construction where they don't. Oh, what am I saying? I'm lying. No. I want to say something else. That basically this there's a different construction. You can construct trees which have unbounded degree, and they have non-linear size Ramsey number. This is in the paper by Moubai, Dudek, Rodel, and Laploch. Okay. And
Liana, actually, just I don't know if it doesn't bother you too much. One comment about the distance. So in powers. So one thing I could imagine for a case power is you join. Isn't there any definition along the lines that whenever you can reach a vertex by stepping along k hyper edges, then somehow from a given vertex, then somehow they must lie in a common edge or something along these lines.
So you could define that way, but we were wondering, okay, so are we gonna do only tight paths, or are we gonna say just any, because this intersection of the paths could be anything, right?
Yeah.
And that basically that would just make our life harder. Because when the intersections are of various sizes. So
that's true.
I agree that it would be a more general definition if you said basically any path, meaning that it's not tight. So the intersections here could be anything at most,
And I mean, like the strictest thing would be having a clique of size k. K r choose k or something like that, right? If you think of it, maybe that's
that would be the strictest. Yeah, I agree.
But that, I guess, would you have your result for such?
But actually, what we prove is something much stronger. So in fact, you can get this. I'll show you the result that we prove from.
Okay, so you can get this.
And I think we are getting what you want as well. But one problem, I mean,
if you increase your power by r times, then you will get what we wanted. If everything is constant, then probably.
Yeah, exactly. So, but also I think just by looking at the main result we prove, I'll show you in a second. Next slide is that.
Thanks.
Yeah. So what was this? This was the right. So this was the powers of trees. And so this is the stronger theorem. So this is not the main result, but it's the stronger theorem from which we get the result about hypergraph trees. So theorem 4 implies theorem 3. What do I mean by this? So take a graph G, and we define this KRG to be an R uniform graph obtained from G as follows. So you take all the possible R cliques of the graph G. So G is a graph, and now you look at it as in the hypergraph setting. You say any R clique I have, I'm going to make it into an edge. So that's how I define this graph called KRG. And what we show is that if you take any tree which was in this family T and D, we have seen this before. These were all the trees of on n vertices and maximum degree D. Then, if I take these trees and I take their Tth power, okay, and then I look at this corresponding this R uniform hypergraph, which is obtained by taking all the R cliques of the graph T to the T, then I get a linear size Ramsey number. And what do I mean by theorem 4 implying theorem 3 is that if I know this, then I can show that this R uniform trees, the way we defined here, are going to actually lie in. So basically, every such T is contained in some. It's not exactly. I don't think you get a tree. I think you get. No, you could. I think you get a tree. It does lie in some T. Yeah. I can find a T such that every hypergraph tree, the way we defined here. What do I want to say? There exists some let me call it S so that it's clear, such that this hypergraph T is contained in if I take all the R clicks in S to the sum power. So there is some S and T. And I think these graphs that you were describing, when it's not a tight path, but it's some path, I think they'll have the similar property.
Yeah, I think so.
Yeah. So so this is what we can prove basically in the tree setting. And finally, for subdivisions, we can also generalize the results. So by the way, all this result I mentioned for paths, powers of paths, and trees and powers of trees, they basically generalize everything that was known in the literature for graphs and hypergraphs. And the same, we can also generalize this result by Draganic, Krivelevich, and Nenadov in only one case. So they had two results, and one of them we can generalize to hypergraphs. So what we can show is that if you take any graph H of maximum degree D, okay, on n vertices, and you ask for your subdivision to be long enough, so it's some constant times log n, then the size Ramsey number for all the colors of this graph is going to be linear. Okay, so what is this graph? The way we are thinking of this graph, it's as just, we are thinking of this as the subdivision in hypergraph setting, but really, this is not a classic definition, so we couldn't find any definition of subdivisions in hypergraph setting, and our proof was giving this, so this is how we formalized it. So I take the Q subdivision of H and I take its T power. So actually it's the powers of subdivisions. So I take the Q subdivision of H and then I take its T power. And then I take all the R sets, R clicks in this graph as my edges, and what we get is that this graph also has a size linear, size Ramsey number linear. Okay. So finally, the general theorem is the following. It says that if you take the following family, so we call it ANDL. So this is the family of all graphs on n vertices, maximum degree D. Okay, so the first, so n is the number of vertices, D is the number of the maximum degree, and L is going to be something else. So what is it? So I want every graph which is in this family to be able to obtain from a singleton vertex by following operations. Either I add a new vertex and I just, so this is whatever I have got at I-1 iteration, and then I add a new vertex and I just join by an edge to one vertex. Or I take my graph, whatever I have obtained at the I-1 step, and then I join two vertices which are already in my graph by a path where the number of these new vertices I add, it's at least L. So you can actually see that, for example, a tree can be obtained like this because every time you are just adding a leaf, subdivisions can also, just for graphs, it's easy to see that you can obtain like this too. Yeah, so what we show is that for any graph H which is in this family, okay, for any edge in this family, where I request that the number of leaves, number of inner vertices when I'm doing this operation, the second operation, is at least of size some constant times log n, then what we can show is that if you take any power of such graph H, so H to the T, and take R clicks of this graph, then their size Ramsey number is linear. And this theorem, so like all the examples I showed, the paths, trees, and this also graph subdivision thing, they are all contained in this. So they can be obtained as KR H to the T. Right.
So for the trees, it's just because you apply only the first rule, right?
Yeah, for trees it's easy to see. For the others, it's not so that hard either. Just I mean, you don't show that they are exactly these guys, but they are contained in some. For some H, they are contained in KR H to the T. So, right, what did I want to say? Okay, so I think this is all the results. Sorry, it's long. It took me basically almost an hour to talk, to get into our main result with the history, but I would like to say some proof ideas, if that's okay.
Yeah, that's okay. I mean, you have well, half an hour, or if you want, if you're enthusiastic, you can take more time. So,
I'm not sure about that, but okay. I'll take okay, so I'll say some things about proofs. Okay, so previous proofs for, say, uniformity 2, for example, let's think. So usually the host graph for these cases of, say, powers of paths or powers of trees, it was obtained as some kth power of the complete graph. So I take an H which has two properties. It's an expander, okay, and it has bounded degree, and then I blow it up by the complete graph KB. So I call this the complete blow up of a power of a bounded degree expander. So what's an expander? If you have not seen it before, there are various ways you can define expanders. The way normally in this proofs one uses the properties of expanders is that if you take any two sets, A and B, so any two sets A and B, which are of large size, and here what I mean by N, it's really the, so this should be omega of V of H. So if I take linear sets of vertices, then there must always exist an edge between A and B. Okay, so any large two sets you pick, there is an edge in between.
so you just need one edge, not
Yeah,
like
I just
many.
need one edge. Yeah, but you can actually, I mean, you can see that it's not just gonna be one. They're gonna be because of this linearity thing. Like,
oh, okay, so it's interesting. So really, for any A and B, this is what
for any A and B. So any.
So for example, if your graph would be bipartite, then you wouldn't have it, even though it may be like. So,
yeah, sorry. So for bipartite case, the way you would define is that A lying in one set and B lying in the other set. You wouldn't ask for, so bipartite expander means that you don't ask for this property for the whole graph, but you say, okay, there's some underlying X and Y.
because I really wonder for the standard, I mean, the standard definition, oh, I don't know, standard, not, you would say that A has some amount of neighbors, maybe say epsilon times the size of A. And what if you take B in the complement to this thing? Because it still can be large, right?
Yeah, but so that's not an expander. So expander means that anytime I take two linear size sets, there must be an edge in between them.
Yeah.
So it's different from this other definition of expander.
Yeah. Okay. Yeah.
So there's so what Andre is saying that there's also this in literature. There's this definition of expanders where you say for every for example, for every set X, if you look at the neighborhood of X, then it's, I don't know, some lambda times X, and so on. But this is not. This does not imply that, because you will have.
So you want a very strict proper, like this, but much stronger.
Yeah,
like with
this is much stronger.
Yeah,
because there is an edge in between them.
Mm-hmm.
But Okay, and then I need to also tell you how do I define a complete blow up. Oops. So if I take any two vertices U and V, which is in my graph H, then in this graph, which I call the complete blow up of H, I replace every vertex by a clique, which by a blob, which is a complete graph on B vertices. So every vertex U becomes now B vertices, B many vertices, and every vertex V, and so on. And whenever I have an edge in between U and V, then I have a complete bipartite graph here in between this. So this is this is how we define the complete blow up of any graph. This is a very classic definition. Okay, so so now how we can actually obtain such a graph H? Okay, so I want a graph H, which is an expander. That one is not hard because as I previously mentioned that you can take the random graph GMP. So the number of vertices here will be some constant, A is a constant, times n. So this is important because you want the number of vertices still be linear in terms of the vertex set of the graph H you are looking for. And the probability P is some B over n, where B is also a constant. Okay, and then what you can do is that you can just remove the large degree vertices from GMP. Another way to obtain this expanders is just to take the ND lambda regular graphs. So these are graphs which are random graphs where every vertex has degree D and the second eigenvalue is lambda. These guys also are expanders. Okay, so so the host graph is obtained as follows: 3 steps normally. You have H as an expander. Okay, so the number of verses in H is of order n, and then you have its maximum degree is bounded. Okay, some constant, and then you take the kth power of H, meaning that whenever 2 verses are of distance k, I add them an edge. I put them in edge in this power H to the K, and then I blow it up by complete clicks on B vertices. So eventually I get something of this form. Okay, and then what is the next step? So now this is
sorry. So the reason for deleting this high degree vertex is exactly so that when you blow it up, do the H to the K, then it would be fine, right?
I mean, if they don't have so B is a constant, right?
Yeah.
But here I need it to be constant too, because even if I have one vertex here of non-constant degree, then my host graph is going to be non-bounded degree.
Yeah. Okay.
What do I want to say in that? It's about the number of edges. So so I think you could have potentially few verses which vary, like, I don't know, constant many verses which have large degrees, as long as it doesn't make your edges to go up. The number.
Yeah. So the only like straightforward reason is that when you take kth power, their effect is multiplied, right? You have to multiply these degrees, and it may be not. Yeah, I don't know.
Well, everything is constant here. K is a constant. This degree is constant, and B.
Yeah. So for this, it's totally good. Yeah.
Okay. So now imagine I'm given any S coloring of the graph HK KB. So now what can I say? So by Ramsey's theorem, so if I look at each one of these blobs BU, what I know is that there must exist either, say, imagine the coloring is just red blue. Inside each blob, this B is large enough. So I have chosen this B such that it's much bigger than the Ramsey number of some KT. Okay, then I know that either there is a large blue clique inside, or a blue or a large red click. So one of these two holds in any as two coloring. Then I pick the majority color. Okay, so what I obtain is that I discard all the non-blue vertices and I forget about the non-majority color. So now I have a bunch of blue blobs, and there are some edges in between. And what do I, okay, so what is now the plan? So right now I know that everything inside each blue click is complete. These parts are completely blue, but I know nothing about the edges that go across. Okay, so imagine if I were, for example, if for example I wanted to like find a blue path in this graph of length n, what I would typically try to do is I would like to try to say, okay, well, if I can connect some vertices going from here to here via blue color, from here to here via blue color, and like, of course, you use these guys to like, extend your path, then you are happy. So basically, we try to connect this sublobes that we found in color blue, going across the blobs. But what if you cannot do this, right? I mean, so what if you are really sparse? In particular, it could be that everything here is red. Then what you have to do is that you have to somehow make your path go across this from blob to blob. So you can't use actually any edge even inside this blue parts. So what you do in that case is that you kind of try to use this sparsity of the blue edges. And for example, here you would find, so if you were doing, for example, powers of paths or just the paths, from here, if this is not the case, what here you would find is that there would be a large, complete multipartite graph, all red edges going across. And these sets would be large, okay? And you would build your path here by some DFS algorithm. Just by using the fact that between blobs there are not many blue edges. Okay.
Liana, can I ask something? So first, you removed, so you only left the blue clicks as the blue. Now blue vertices are actually these blue clicks, right? Meaning every edge between them. And also, when you say this complete multipartite graph, what exactly do you mean? Because we had a graph that was like linear edge density, so you wouldn't expect any like complete not necessarily any complete multipartite graphs in it to begin with. If so, at least the way I understand it.
No, but you can still expect, right, that I can find, okay, so what I'm trying to say is that I will find large sets here such that, okay, so I see what you are saying. I'm skipping lots of steps because I go to some auxiliary graph, basically, in between and stuff. So this is what, and the auxiliary graph is supposed to tell you, it's supposed to code what's the color of, say, so for example, for powers of paths, you would say, if there is like no small blue click inside going in between these two, in an auxiliary graph, you are going to color this edge by red color. Otherwise, you are going to color it by blue color.
But my problem here is that like very few vertices are actually connected by, like initially you started with a linear sized graph and it had linearly many edges. So like it's constant degree graph, and then you blew it up.
But what you get is that I can, in the original graph, you can imagine that what you are finding, if you cannot find this path, is that you are finding a bunch of blobs, which are all the edges that go across are red.
Yeah.
And then you use this red edges to build a red path.
Yeah. But this auxiliary graph that you're talking about, is it like these vertices are essentially the same vertices of the graph before the blowing it up, or?
Yes, you can think about it like that. Yeah.
But then it has linearly many, like its number of vertices and number of edges is roughly the same, meaning it's one is constant times the other. So there, so what exactly you do in this auxiliary graph, even if it's all red?
What you do is that then you use the auxiliary graph, and then you go back to this graph and you try. So because I know that there is a red edge, it means that there are lots of red edges that go across.
Yeah, but how do you find the path in that auxiliary graph? I mean, not
in here.
Yeah, in this.
It's another Ramsey like result because.
Okay. So you're using a Ramsey result for.
Yeah, I use it twice basically. So when I go to the auxiliary graph, I have some auxiliary red-blue coloring, which is encoding this previous coloring. And again, I know that it's not the classic Ramsey thing. It's now like the complete multipartite graph versus something else. So it's, I think, versus a path. So because I either want the blue path or I want the complete multipartite in red color, such that I'm gonna be able to find my red paths. So this is basically the proof for the powers of trees or powers of paths.
Okay, roughly.
Yeah, roughly.
Thanks, Liana.
So right. So, but you can imagine that, for example, when the number of colors becomes larger, so already for more than 3 colors, this becomes much more ad hoc, because the moment I don't have any, so in the 2-color case, it's easy. You say, okay, it's either one color or the other color. In the 3-color, okay, now you have to do more stuff. And all the methods which were doing things for this multicolor case, they were quite ad hoc, like meaning that from problem to problem, from graph to graph, it was different. Okay. Now, idea number 1, the new idea number 1. Okay, I think like this is probably, if you can take away one thing from today, from the ideas, I think this is nice, because this is also probably the only idea that I can explain properly without being technical. So our host graph is going to be the following. So just like before, we are taking H, which is some expander. I take some power afterward, and then I blow it up by B vertices. And now, and then I take all the R clicks of this graph, and which gives me some R uniform hypergraph. Now, again, so this is the analog of the previous lemma, the first step, but it's actually much stronger. So we can show that in every so this is a Ramsey type result. It says that so it's lemma. In any S coloring of the graph G, so my host graph, I can guarantee to have a subgraph of G such that all the edges of the same type have the same color. What do I mean, edges of the same type? Okay, so my G is, so this graph here, HKB, is something like this, and then in the graph setting. And when I take all the R clicks, I basically, you can imagine that inside these blobs, I have complete hypergraphs. Every R edge is here as is present. Every R set is an edge in this graph. And then in between the blobs, whenever I see an R click in this graph, I put an edge. Okay. Now I give any S coloring. What I can guarantee is that if I have 2 edges which intersect the same blobs the same number of times, then these edges are all of the same color. So what do I mean by that? So if I have in def, I'll say that they have the same type if for each one of these blobs, BU, if I look at the intersection of E with the BU and F intersection with BU, then it's the same cardinality. So for example, what I can guarantee is that all the edges which have 2 vertices in this blob and 1 vertex here, they are all pink, every single one of them. Okay, or all the edges which are inside one blob, they're all of the same color. Or all the edges which have, say, 1 vertex from this blob and 2 other vertices from this blob, all of them are green, any edge I see of this form. And for example, if they intersect this blob in 2 vertices and this blob in 1, then they're all red. And this I can guarantee, like, it's much more universal thing than the previous result. In particular, it already tells you that all of these guys are completely monochromatic, but much more, right? So like, you know now much more about the edges that go in between.
So before in the 2 case, it was really just the edges inside each blob that you wanted to have.
Yeah, and here, so it tells you actually, so like if you do that, so in the difference, for example, between this and this guy is that for example, for graphs, it would already tell you that, so I can just look at, so for example, this was the graph case. The lemma tells you that I can find sub blobs inside. So, okay, maybe imagine that these were my bigger blobs, and then I found some sub blobs such that basically all the edges that go from blob, say 1 to 2, they're all blue. All the edges that go from a blob 2, say, to blob 3, they're all pink. And then I also know all the that these guys are all monochromatic.
So it definitely simplifies you this case analysis before.
Yeah. It's completely makes it much easier. Yeah. So on, you know. And for hypergraph, it's also very useful. Yeah. And this is like a Ramsey type proof, and you prove it by using. So the way you can do it is that you can first think about, say, like one type of edges, you know, and you can kind of trim down further. And so what I want to say is that I can keep shrinking my graph until I get to the blobs which behave this way. And it's like an iterative Ramsey argument where you where you keep reducing the number of colors each time. It's like for one color you get everything, so 2 colors you get nice things, and then you go to the next, you add 1 color and you can also provide that, and so on. Okay, so but yeah, so this is one important part. But what it tells us is that the main advantage of this is that instead of looking for a tight path, for example, now I can look for a tight walk. Why? Because essentially every single vertex which is inside a blob, so these are my subblobs, these guys are my subblobs. This result tells me that all the subblobs are actually, every vertex inside the subblob behaves as if all of them. So they actually interchangeable, which means that instead of looking for a copy of H, I can look for a homomorphic copy, where now I think about this subblob to be as one vertex, because this blob behaves, no vertex in this blob behaves differently from another. Okay, so this tells me that.
But you still somehow have to control, like, not to use one vertex too many times,
yeah,
right?
Very good. Yes, very good. Exactly. So I want to I'm happy to use to find a homomorphic copy, but I don't want to use any because these sublobs are all of size constant. So I cannot use I cannot have too many vertices mapped to one vertex, which corresponds to one blob. So you're right. So the new setting would be that I would like to find an S coloring. Yeah, so I'm given now an S coloring of a different graph of the KRH to the K. This is an auxiliary coloring which I derive from previous graph. So previously I was given the coloring of KRH to the KB. And after doing this first Ramsey argument, I get some auxiliary coloring of this graph, which is, I forget about the blow-ups. Yeah, and then I'm looking for a homomorphic copy of my graph H, such that every vertex is used constant many times. And of course, whatever times I want it to be something like B, which is much smaller constant than the overall complete blow up size. Okay. Now, another idea, okay, and here's where things are going to get vague, is so for hypergraphs, what we need to do is to so what we do is for every vertex in our host graph. So I don't know why I said H, and yeah, so H is my host graph. Right, so H is the original expander that I took, but the vertex set didn't really change. If I look at G prime and H have the same vertex set. So for every vertex in this graph H, I'm going to assign an ordered tree, which is, and what is an ordered tree? It's a tree that's drawn in a planar way, meaning that there's like an ordering on the leaves, okay? And what I want is that, it looks like this. It looks like a planar drawing of a tree. It doesn't look like this. I don't have cross edges going. So I don't have this 1, 2, 3, 4, 5. You see? So it is actually important that we think about, we take ordered tree rather than this, guys. But this is like a technical detail. Okay. And for every vertex in my vertex set, I assign an ordered tree to this vertex. And this tree is such that the leaves of every tree live in my graph as well. So it's like the leaves that you see here, they are part of the graph H. So it's like you have the uniform hypergraph, but then on top of it also there's like trees which every vertex is assigned to, and their leaves are living on this graph vertex set still. And then there is yet another auxiliary coloring we take, and it says that so I'm going to color two vertices, the edge between U and V. So this is an edge this is going to be like some edge in G to the K, and this K is going to be different K. It's going to be like it's a bit difficult to say this part, but basically you take any UV edge which appears in some power of my graph, and then I color it by specific color C if there exists something which I call connector between the leaf sets of color C. So I'll explain what this means in a second. But what it tells me actually is that, again, a Ramsey type argument shows that either you are, after doing this, encoding everything via trees in some power of G, you can either find a long monochromatic non-gray path in this auxiliary coloring, or you are going to find many gray clicks. Okay.
And what is gray?
So gray means that you cannot jump from. So it means that you cannot go from. That such a connector does not exist. That you cannot actually build. You cannot jump from one tree to another by some nice way.
Okay.
It's basically. And jumping here means that in the original coloring, you do not see any you do not see, say, for example, a path of a specific, of any color, monochromatic path of, say, a certain color that goes from one leaf to the other, from one leaf set to the other. That's why you colored it gray. So what happens is that in the case one, when we find this long monochromatic path of some color, we can lift it to path. So I'm thinking about like the tight path case, for example. Then I can lift it using these connectors to find a tight path in the hypergraph. In the case two, when I find this monochromatic gray bunches, what I end up doing is I end up extending my trees. So originally these trees are just singletons, and then in each step I grow in height in this tree. So I keep building larger and longer and longer trees. What a connector is, it's something like this. So for an edge UV, I would say in some power of g to the k, I would say that there exists a connector. If there are three vertex at x, y, and z, such that if I look at x union y, then it's a monochromatic click in the original hypergraph, in the original coloring. If I look at y union z, it's also monochromatic. Additionally, what I want is that this x is lying in a leaf set of some tu, and y is lying in some leaf set of tb. And there's also something else I want. I want that these trees have that if I follow all the verses that are in x, and so the whole thing lies in tu, and then so there's like some tu here that's taking of this. Oh no. So there is some, the best. So there is some tree tu which contains all of this x. Imagine all of this guy. What I want is that if I look at just the part which is, so this tu can be much larger, right? But what I want is that if I just follow the vertices of x towards all the way when they meet a common ancestor, I get some tree. Let me call it T1. Then what I have is that if I do the same for z, then T1 and T2 are isomorphic. Okay, so why am I going to want this? Why is this important? It's because we can prove some Ramsey type properties of ordered trees, meaning that you kind of look at this hypergraph and you color your copies of trees. And when you can prove in a Ramsey type result, which says that you can guarantee that whenever you have, basically you can say something like that all trees which are isomorphic, their edge sets corresponding to them are going to be monochromatic. What it is going to allow us to do is it's going to basically allow us to jump from this part to this part in the same colors. Basically, that's what I'm going to be able to do to guarantee that I can actually find monochromatic paths going from here to here. This is the takeaway, basically. And then when I have a bunch of these connectors, I have found, so like I have found a large non-gray path. What I can do is that, so on one step, maybe I think it would be good to draw a picture. So imagine I have found some path in this auxiliary coloring. And this, in the easiest case, say like r equals 2, is going to mean that I have like bunch of blobs, and I can go from one blob to the other blob in the same color, okay? And then from this guy to this guy from the same color, and so on, okay? So this is in the R, so like R equals 2 case, this is what you get. But now what's like the next question is that you kind of want these guys to be the same, right? To be able to find a red path. And you can do that because for example, you know that, so what do I want to say? In the R equals 2 case, this is actually quite easy, just because you can say that, okay, everyone here has the same color, so it doesn't really matter, and everything is also complete here, so it doesn't matter what I do. But for when R equals 3, this is when you need the trees, so that you ensure that if you have sets which have the same trees, like lying on top of them, you use them to kind of say, I can actually merge these guys by using this Ramsey property of the ordered trees. I don't know, this is a bit hand wavy, but yeah, it is quite technical to present this part. So and in the other case, when you get this gray monochromatic path, what happens is that you now can make even like new trees. And so your trees become taller, but their degrees decrease. And eventually this process has to stop, because this you will basically run out of colors. This will be impossible to maintain this property. Okay, so I think that's roughly what I wanted to say, and then I will end with 2 open problems. One is there's this graph called grid. A grid of size n by n is the following. So you take, it's just n by n grid, meaning that 3 by 3 is that you take 3 rows, 3 columns, and intersections are vertices. So what is grid? Why is this grid interesting? It's okay. So basically, by our result of that the Size Ramsey number of powers of paths are linear, it also implies that the Size Ramsey number of all trees of bounded tree width are linear. So of all graphs of bounded tree width. And this is something which is in structural graph theory, tree width is used. So it's a parameter which is used in structural graph theory. And the grid is the simplest example which has unbounded tree width. So it could be interesting to actually think about whether this guy has a linear Size Ramsey number or not. And this is a result by Schacht, Taras, Clemens, and Redding shows that the grid has a Size Ramsey number n to the 3 plus little of 1. But of course, the question is, okay, what's the truth in between these two? Is it linear, meaning that if it's n by n grid, I have n square many vertices? So the question would be, does the grid have linear Size Ramsey number or not? Or actually anything. Can you improve this little O1 here? Can you improve this? Just get 3 to the minus epsilon, really? Like anything would be useful. We don't know much about this here. And this here is obtained by the random graph. So of certain density. So you can improve maybe this using like a better understanding of the random graph. But if you want to get something of order n to the 3 minus epsilon, there's no way. Okay, so yeah, that's one question, very interesting, I think. And the Rodel-Semeradi conjecture, meaning that we don't know, so basically, do there exist graphs H of bounded degree such that the size Ramsey number is, say, omega n to the 1 plus epsilon. So far, we know that it's like n times log n to the some power. This is one question. And second question is examples of other graphs. Bounded degree, such that the size Ramsey number is not linear. So far, we only know of one graph, basically. I think that's all. I'm very sorry. I'm even later than the.
That's totally fine, Liana. Thanks a lot for the talk. So, are there any questions from the audience? Tao, or?
I don't know. I hope Tao is not sleeping.
Yeah, but because he's
what's known about the regular Ramsey number of the grid? What's known about the regular Ramsey number of the grid?
Well, I mean,
it's bounded degree.
It's bounded degree, so it's linear.
Oh, okay.
So the normal RH is normal RH is of n square, which means that it implies that the size Ramsey is like of n fourth.
4 trivially, yeah.
And then the random graph gives you n to the cube.
Yes.
Actually, here, Liana, I wanted to ask. So for this Hvatal and company result for this normal Ramsey number, so there is this regularity proof. Is it essentially the only proof we know, or?
Yeah, that's actually. You mean? I see what you are saying. You're asking
For this graph, for example,
whether there's any other way to see why it's say n to the fourth rather than going through the Ramsey number. That's what.
Or no, even just for the normal Ramsey numbers, I was wondering: is the only way that we know how to prove, say, this fact that the R of this graph is linear, is by going through this blow-up lemma, in a sense, in regularity?
Yeah, as far as I know, yes, but that's an interesting question. Actually, we were at some point, I think, wondering about this. I think Asaf asked, so like something about just saying for which graphs you can give some general bounds which will not have to go through this normal Ramsey number.
Because it may also give a different perspective on all of this, because if you use regularity, it would always be like Ramsey number squared order Ramsey number squared. So it's good.
Yeah, we don't know much there. In general, I think the size Ramsey numbers are not well studied. Like we don't really know much about them. But yeah.
Okay. Any more questions? Well, if not, Liana, thanks a lot, and it was very interesting. A bit dense at the end.
Sorry about that. Yeah, no, I tried to make it as not dense as possible, but
I mean, this is the way it is.
I still have to figure out how to say the last parts better. So that is it.
But in any case, impressive, very impressive result, I think. So yeah, thanks a lot, and hope to see you sometime soon in real life.
Hope to see you too. Take care.
Yeah, you too. Bye bye.
Bye everyone.